there is a difference of opinion about what is dispersion in a groundwater system. Some people say that dispersion is nothing but the effect of the unmodeled heterogeneity or tortuosity. That means what happens is that when you are looking at having a macroscopic view, as I said, I am saying I am not differentiating what type of, you might have some triangular elements, you might have large elements, some of the smaller ones, and then how the pollutant might be traveling inside will depend upon in many ways. That what is the arrangement, not only this grain size, but also the arrangement of this, and it might travel like this, it might travel like this, it might travel like this, and go out of this face or something like this. So, because of that only, though you might think that it is releasing some pollutant over here, and it is just coming out at this phase over here, that is not true. It is actually following a much larger path. So, dispersion might occur just because of the grain structure, the heterogeneity of the grain structures and the tortuosity of the path. How tortuous the path is, it goes like this, like this, like this. When you are macroscopically looking at it, you say, okay, this is the area, this is the volume, you are releasing something over here. What do you see over here? You are not looking at the microscopically how these particles are actually going through the system. So, dispersion might be, and as I said, there are so many schools of thoughts about this, and it might be that just it's due to the unmodeled heterogeneity in the molecular scale or microscopic scale. So, the dispersion is effect. So, sometimes dispersion to measure in any system is very difficult, okay, and I will come to that, but that is something which actually is more of a first factor, that is you try to get the right answer by adding some dispersion term, so that what concentrations you are finding matches what you see in the field, okay. So, that means you are artificially using some kind of mixing process which does not have a very good explanation exactly what it is, okay, dispersion in groundwater system, okay, because there is no turbulence really. So therefore, some people call it first factor. Another thing, maybe those who will be doing some modeling and who might be interested, I will also say that generally the dispersion coefficient, will come to that, will depend on the scale of your model. If you are looking at grid size which is 1 centimeter by 1 centimeter, maybe the dispersion coefficient might be like if it's 1 centimeter means maybe half a centimeter, okay. If your scale, your discretization is, you are using grids which are 100 meters by 100 meters, the dispersion coefficient might be about 40 meters or 50 meters, 0.4 times, 0.5 times the size of the grids. So, that is very important. So, therefore, it is something which is numerically also influencing the process. So, therefore, because if you do not have this dispersion coefficients which matches with the scale of your discretization, that means you have a study area like this, you divide into number of grids, that is what is known as discretization. It might be finite elements also, that is a different thing, I will maybe discuss a bit, but finite difference grids like this. So, you basically make it look like this type of system, maybe like approximately this is looking like this, and maybe like this, and maybe like this. So, that is how you are discretized into number of grids, each is maybe delta x, this is delta y. So, if delta x is equal to say 10 meters, your dispersion coefficient will be maybe 0.3, 0.4 times of this, maybe 4 meters. If it is 100 meters or maybe 200 meters, it might be maybe 80 meters or 100 meters dispersion coefficient. If you do not do that, your numerical solution may not actually be stable, or it may not be even accurate. So, that is one thing. So, your numerical solutions will depend upon what type of values you are assuming for the dispersion coefficients. That is very much dependent upon the scale of your study area and the scale of discretization. So, that is what it is. And I have seen many times that if your dispersion coefficients are wrong, this solution is not very stable or not very accurate. Okay. So, that is something you have to be careful. So, many people say that you can actually do not have to consider it, you can actually numerically introduce some dispersion into your numerical method and it will take care of it. Maybe that is true, okay. But it has got some explanation that it is, I like this one, that because actually the path that is traveled by water particle is very different from what we think is coming from this point to this point. It is not like this, it is coming like this and here and here and coming out here. So, there will be mixing, okay. So, that is what it is. So, anyway, so this is advection. Of course, you understand that if I just drop this piece of paper in the water, so you will see it will be floating like this over here, then there. So, that is really advection, okay. So, the moment this gets mixed up with the water more, So, you have this diffusion and dispersion. So, one of course, a molecular scale, one is larger scale. So, advection and this. So, this should be very clear. Now, I do not know why. This is what it says. The dispersion is like a packet. If you are releasing a packet over here, you almost see the same packet after some distance. No, it is like a packet. It's nothing is getting mixed up. Okay. It's almost like putting something. So, advection movement of chemicals into the current velocity. So, if the velocity is here, you release it over here. After some time it will be here. After some time it will be here. After some time it will be here. This might be the concentration. This is like a plume. No? The concentration is maybe, I don't know how much it is, 400 maybe milligrams per liter or something like this. So, it is so T at T equal to T1, it is here, T equal to T2, because the water is moving. So, it is over here. After some time T3, it is here, T4 is here. That is your advection part, nothing else. Very the simplest, but I will also say that is the major component of the transport process, because maybe 70-80% or even sometimes more of the pollutant or the contaminant will be carried by the process of advection. So, that is very important. Okay. Other parts are relatively smaller. Now, if I use this, so that means you are releasing something in the water. Suppose the velocity is u bar or something like that of the water, and how much is coming out of the other side. So, I take a volume like this, maybe it is almost like in half a cylinder. What is coming in is u bar is the velocity, and over here what will happen. So, this distance is between A, this point is A, or this section is at A, this is equal to B. So, we can write this the missing yeah. So, I cannot reduce this one. Yes, actually I do not know how it got. Somehow this, I think we are transferring this some of the things electronically, and this words got actually all mixed up. So, it is very difficult to read. Mass in the control volume at any instance is equal to V c. So, that is, volume is the V, is here, V is the volume, C is the concentration. Change in the mass. So, therefore, let us say, so initially in the control volume, again is elemental volume or control volume. So, V is the volume, C is the concentration. Why? Because concentration, the unit of concentration is milligrams per liters generally. Okay, that is mass per unit volume. So, this might be milligrams per liter, it may be something, it can be kg per meter cube. So, all these things are possible. It is basically mass by volume, so the m by L cube. Okay. So, that is the concentration. How you describe a contamination is in terms of concentration of a contaminant or pollutant, and so the volume is equal to V multiplied by C will give you volume into the mass per unit volume. Okay. So, that will give you the mass, so V into C. So, therefore, del V by, so if you look at delta V C, that means that is equal to change in the mass within the control volume. That is a change, delta is change, stands for change. So, that is change in the mass in the control volume. Okay. So, this change in mass will be nothing but, now if the concentration that is coming in is actually Ca and Cb. So, at this, this is I will not, maybe it will take some time. If you, it is not anyway. So, let me just draw it in this section over here. I am not very good in drawing, and so basically like something like this. And here it is Ca, the concentration here what is coming out is Cb. Is not a very good drawing, but anyway this is the one is Cb, and this section is A, this section is B. So, what is coming in is Qa, and Qa is the discharge rate of flow or inflow, and what is coming out is Qb. So, the mass, the rate of mass coming in is actually Qa into Ca. Why? Because Qa is nothing but volume per unit time, that is what is coming in. So, multiplied by mass per unit volume. So, that will give you mass per unit time. Okay, mass per unit time. So, that is Q into Ca is the what is coming in. Similarly, what is going out is Qb into Cb. That is the concentration over here. Okay, that is Cb that is coming out, and Qb is the discharge rate, again mass per volume per unit time. So, therefore, this is the rate per unit time. So, I multiply by delta T, that will give you how much of the mass the net mass is coming in. This is how much is coming in is QA into CA, what is going out is QB into CB. The net mass coming in is QA into CA minus this. So, in time delta t, this is the how much mass is actually coming in, because this per unit time. Okay. So, therefore, I multiply by delta t. So, because per unit time, then you multiply by delta t, that gives me the mass. Okay. So, then this I can say that this is equal to change in the mass within the control volume, because again the same principle, mass conservation. So, what is the net mass inflow is equal to change in the the total mass within the control volume, and that is given by this delta V into C, as I said before. Okay. That is it. And if you agree with that, then you can, I hope you can, hope this equation is given. So, you can actually do some simplification, this and that, and of course, I can use V is equal to A into delta x. What is this distance is delta x, and cross section area is A. So, A into delta x is equal to, so if you take a section, this section is equal to, cross section area is equal to A. You can say the volume is nothing but delta x into A. So, that is what is the volume. So, you can do all these things, I will not go into it. So, ultimately, so this is using this equation basically, and then using this information that volume is equal to A into delta x, you can actually get this equation. So, del C by del T, and here I am looking at change in mass within the control volume. So, obviously, it is a transient condition, it is not a steady state condition, because storage is changing, how much mass is stored inside the control volume is being changing. So, I get this equation is equal to minus u actually. So, u is the of course the velocity. So, this is q by A. So, that is how it comes, because I am using this, I replace this V is equal to A into delta x. So, I can write the delta A is now included, and if you remember q by A will give you the velocity, because this discharge, that is the volume per unit time divided by cross section area, that gives you the velocity. Okay. So, that velocity term will come. So, you can this this it will come, it will. So, this equal to minus u del C by del x, and again this do not bother too much about negative sign, it depends on whether x is increasing, where concentration decreasing on. So, therefore, the increase or decrease. So, that will take care of the sign. So, that is never, the mass is never negative. So, that is what it says. So, that is why you introduce this. So, then del C by del T will be equal to minus u del C by del x. So, it is just from this mass balance condition, taking unit just an elemental volume or control volume, using mass balance equation, and this some small manipulation over here, using the relationship for volume equal to A into delta x. A is the cross section area, and delta x is this distance basically. I can come to this equation del C by del T. So, what does it mean? So, and this is the advective transport equation. Okay. That means change in mass, change in concentration with respect to time is given by, of course, forgetting about the negative sign, is the velocity or the average velocity multiplied by the concentration gradient, that is del C by del x is the concentration gradient. Okay. So, change in C concentration with respect to x in the x direction, that is the gradient, how C is changing. So, I am getting this, and this is because I have only considered advection, nothing else. So, this is the advective transport equation. It tells you how the concentration will change with time when the gradient is known, or for a given gradient. Okay. And if you know u bar, it will tell you what will be the concentration. Actually, now C is a function of both x and t, because C, what is say del C by del T is equal to del C by del x. So, C is considered as a function of both x and t. The solution of this equation will give you now the concentration at a given location at a given time. Okay. So, the solution of this equation, which is the partial differential equation, which is the governing equation for advective transport really, and then solution, if you could solve this partial differential equations using numerical methods or analytical methods, that solution will be C as a function of x and t. That will give you what is the concentration at different time and different locations. Okay. So, that is it. So, if you are using, so therefore, this is very fundamental. So, this is so now you have a study area. Okay. You take any study area. So, the some concentration is at this point, you know that you have injected something, and then the concentration is known at this point, you know the plume. You want to find out what will happen what will be concentration at this point or any location, maybe this location, this location, this location, this location, at different, so that means at different locations given by, here I am using x, and at any given time t. Now, of course, if you consider is x and y direction, it can be C can be function of x and y and t. If you consider even x, y and z direction, it means C can be function of x, y, z and t. Is by analogy, it is very similar derivation. I am not going into it because you can always extend to 1 dimension to 2 dimension to 3 dimensions. Okay. That means solution of this equation will give you the concentrations at given location, especially here, and also if you go downwards, maybe different layers, and if it is possible at this layers and this layer. So therefore, whatever location, the solution of this equation will give you the concentration. Okay. But of course, you have to solve it. And how can you solve it? Again, using either analytical methods or numerical methods. In the early 80s, up to early 80s, the middle of the 80s, everybody tried to get analytical solutions. Okay. Or analytical methods, or which is known as the exact solution. Numerical methods, always you have to discretize, it is approximate, because in numerical methods you always say, okay, del C by del x is nearly equal to delta C by delta x. That means, and what does it mean? That if you have a grid like this, anyway, so any grid like this, so I know maybe this point is C1, this point is C2, and this is maybe x1, this is x2. So del C by del x is approximately equal to delta C by delta x. That means, when delta x tends to 0, it becomes del C by del x, which will be nothing but equal to del C is nothing but maybe C1 minus C2, or the other way, divided by delta x, which might be this x1 minus x2 or something, okay, or delta x as it is. Okay. So therefore, I am approximating this differential del C by del x by del C1 minus C2 by x1 by x2 by discretizing the study area into this, grids or blocks or whatever it is like this, and then saying, okay, I can approximate at this point what is del C by del x. I can say, okay, looking in the forward direction, C2 and C1, maybe I can say this del C by del x at this point is this one. At this point, you can also find out in terms of the other grids over here, maybe you can find out. And also, last time I explained del square C by del x square you can find. So that is nothing but del C by del x at point maybe 2 or 3 minus del C by del x at point maybe 1 divided by the distance between them, delta x, or 1 by delta x. So you are trying to find out this del C by del x at this point 3 minus del C by del x at this point 1. Then you are trying to again using, because it's del square C by del x square, you are again dividing this difference by del x. So here you have divided once by del x, you are dividing once more with del x, and that will give you nearly the value of del square C by del x square. If it's second, second order differential equation also, you can approximate this by this thing. So now there is, of course, you are saying that that this is only true, and this is what is the important point, that del C by del x is equal to del C by del x, which is the change in C with respect to del C, change in x, and you can discretize the study area and say this del C is nothing but the value of C2 and C21 difference between these two. But that is only true when delta x is very, very small. That is true. So because by definition that this differential del C by del x is actually when del C by actually this by this when delta x is tending to 0. Okay, that is very, very small, infinitesimally small. But in numerical method, what you do, it is not very small. Sometimes it is depends upon the grid size. Okay, it may be grid size. If you are modeling a 1 kilometer by 1 kilometer area, maybe 50 meters grid is okay. Okay, but if you are modeling maybe 10 kilometers by 10 kilometers, maybe sometimes you have to go for 100 meters grid size. Okay, but then I will come to that. So but accuracy will be better if delta x is small, if the discretization is small grids. Okay. That is very important. It should go as small as possible, depends on many other issues, but the problem is the moment you make this discretization very, very fine, there might be some other kind of instability, okay, in the solution. So it may not always be, so somewhere there is a compromise, okay, or trade off. So you might have to stop somewhere. Maybe 1 centimeter by 1 centimeter grid might give you very accurate results, but actually it won't, because it is too small. Okay, so this you have to be careful. So Now, another question which I forgot to mention also, analytical, what is the analytical method? That means, because you have a very simple that this differential equation, and if it is one dimensional, very simple system, boundaries are like rectangular, not like this and this, and so you might be able to get a closed form solution, okay, exact solution, theoretical solution. You do not have to go for, but the moment you go for even two dimensions, sometimes possible, 3 dimensions almost impossible. You have to go for numerical methods. And if you do not have very nice boundary which is rectangular study area and but is irregular, this and that, all kinds of things, analytical methods do not work. So, as now analytical methods are almost going out of fashion, and also the power of the computer is so much you can solve very large problems, which was not possible in the 80s. Some of the problems we used to solve take about 3 or 4 weeks in a computer when nobody is using that computer, so in mainframe. So, but now you can do it in a PC laptop within 1 or 2 days. Okay, so the power of the computer is now unbelievable, and it is going by growing exponentially. Anyway, so this is what. So, del square also you can find out. So, even if second order, I will come to the second order equation right now. So you can do this and convert into a number of. So, what happens by this numerical method is that you are converting this finite difference, you are using this partial differential equation, converting into what we call finite difference equations. Okay. Simply because you are replacing del c by del t, which is nothing but del c by del x, which is nothing but del c by del x, or delta c by del x when delta x tending to very small value, which is an approximation, but is actually you are taking a finite difference between this, not really is almost 0. Delta x never almost 0, it is maybe 10 meters, 100 meters, so it is actually not 0. So therefore, it is called finite difference. Okay. It is not infinitesimally small, it is finite difference. And by writing this equation at this point and this point, you can write this, what is del c by del x at this point and this point, this point, this point, this point. And suppose this and also you can use the whole equation, advection equation also, like you can write also del c by del t, but here the discretization has to be not in terms of x, but in terms of time t. Okay. So you can write all these things. So then one axis might be x axis, one axis time axis. So then you have to start from somewhere, the initial point, what is at t equal to 0. You should know what was the value of the maybe c at t equal to 0. Otherwise, you cannot go to t equal to 1, you cannot go to t equal to 2, t equal to 3. Okay, that is very important. So therefore, because del c by del t is here, that means there is change of concentration with respect to time, and obviously it is a transient equation. So you have to give the initial conditions. So what is the state you are starting at t equal to 0? So you have to give the value of c at t equal to 0 at every x maybe. Otherwise, you are not defining the problem, you cannot solve it. Okay. So that is one thing. And the other thing is, so now you can therefore I can consider t as another axis and x as another axis. Of course, if it becomes x, y, z in the 4 axis, so it is difficult to visualize, but suppose this one axis x equal to t, and you are writing this equation every node, so in terms of t and x. So then what will happen? So this equation I can say that means del c by del t, you should take the minus sign over, plus u and del c by del x is equal to 0. I can write is equal to this equal to 0. So every node I can write this equation equal to 0. So then what do you have? You have a system of algebraic equation. Okay. I'll probably give you the example afterwards, but that at this point, if you write this condition, this you approximating this, you will have this equal to 0. So you can write it down. So you can have one algebraic equation. At this point, you have one algebraic equation. You have algebraic equation. To solve it, of course, you have to know the initial condition because t is involved. So where do you are starting from? And also you should know generally the values at the boundaries, because if you do not know this, you will not be able to solve it, or it might be infinite. Many solutions are possible which satisfies the equation. Not one particularly is suitable. Okay, so many solutions will be. That means you have not defined the system, your study area, unless you are given the boundary conditions. And last time I said boundary conditions might be specified head, specified flux, or no flow boundary, that means flux is 0. So all kinds of things are possible, but if once you specified means it is not calculating the values at these points, but is already given. Okay. So that means if once it knows these values, it can probably use that information to find out what is the value over here. Okay. So it needs this value and this value, then, and once you know this value and this value and this, you can probably find the value over here. So ultimately what is finding? C as a function of x and t. Okay. So that means you are converting a partial set or a partial differential equation into a discretized set of algebraic equations, simultaneous equations, because for every node you can write this equation. So, you have no, so how many variables are there and how many equations there, it will be should be okay, but that will not be equal unless you define the boundary conditions. So, if you have not defined the boundary conditions, your system is not defined. Okay. So, that is very important, and I will discuss some of these boundary conditions. I have some examples later. So, I think I will address your concerns, but I can discuss some of this also without showing this example, but anyway. So, this is very important. So, the whole idea of numerical methods is that convert the partial differential equations into system of simultaneous algebraic equations and then solve it. Even if non-linear, it can be solved. You can use some iteration method. So, there are inverse matrix inversion methods, and these methods, all kinds of methods are there. I will not go into it because that's and as I said, most of the times you should not, if you are doing a PhD, you may not, but I think in your case it might be different. But you don't write the solution yourself, you might be using some packages. So, but if you are developing, of course, you are specialization in numerical methods, so that's a different issue. Okay, so there also, so therefore, so you understand. So that is the, so any partial differential equation can be converted into a set of simultaneous algebraic equations, and once you have algebraic equations, you can solve it. Okay, so many methods. Okay, so that is the whole idea of numerical methods, nothing else. But you have to define the system, both initial boundary condition necessary, and so the advection part is very clear. What happens? You have dispersion or diffusion. So the moment you have diffusion, so suppose the plume is looking like this. Okay, concentration is 1 to 100. You have just put something. You took a bucket of some pollutants, just dropped it over here, and suddenly concentrations become like this. Now, small area is like this. Okay, so if you had only advections, it will be like this as before. It will be like moving like this, like packet. So you are maybe dropping this page over there, and is going like this and like this. Just with the velocity. Just sometimes you float a boat or something, is moving from this point to this. That's advection really in some ways. So here, but if you have diffusion, so that's additional mixing process. Now some mixing takes place. So obviously that may be molecular scales, not very important, but then still I have exaggerated a bit. Then you can see what will happen. It will start. So at T2, maybe at time T2, it will be even at the same place. Maybe I am assuming there is no velocity. So, I am assuming the same point x. Okay. So, T1 it looks like this, just like a impulse or something like that, like it's 100 over here and nothing here, nothing here. So, this is like this, and then suddenly it starts spreading a bit. Okay. So, you can see it is not a rectangle plume like this, it is over here, it started spreading. So, instead of this, that's after some time it will start spreading like this. Okay, maybe because of diffusion, the molecular scale, the molecular mixing, they are moving around, it's like this. So, but more importantly, even the peak concentration will come down, because it is generally, I mean, not that always it should, but I think most of the time it is, there might be some exceptional circumstances. The peak concentration was here, but because it's spreading, so it is the peak concentration is here and not here. Okay, so so it comes down a bit. So the maximum concentration is also coming down because of diffusion, though it's spreading over a larger area. And with time, it is because it's spread over here, then it's spread over here, spread over here, spread. You can see maybe from 100 ultimately at T6. At time, maybe few hours or something, it is only 60 or 62 instead of 100. You can see, though it is now covering a larger area, instead of this, it is covering a large area, but the peak concentration also comes. So that is the effect of some mixing, whether it is a molecular scale or it is in the pore scale, which is dispersion also. So dispersion has got very similar effect in this exaggerated. Now I just put the turbulent diffusion is not a part of this thing, but when you go to the surface water, I wanted to show maybe the same packet, because there is a velocity variation in a river. From it is almost 0 at over here, and also it is maximum near the surface, not really maximum at the surface, but slightly below that. And because there is a velocity gradient in the vertical direction also, that gives rise to some more mixing process. Okay. So this has nothing to do with groundwater system. I just wanted to show you this. Okay. So don't confuse this with this one. So because in a river you will see the velocity is almost 0 near the bed, and then it goes, but it slightly becomes near maximum, the velocity distribution parabolic and it becomes like this in a river or something. It's not maximum, it's somewhere over here at 0.8 or 0.9. Okay. So, anyway, so that gives rise to that velocity variation also gives rise to some dispersion. Okay. So, now if I combine the effect of advection and diffusion and dispersion, so what will happen? So, dispersion can be a more exaggerated mixing process, okay, and diffusion. So, suppose this is the plume over here at time t at distance x equal to 0. Now, there is advection. So, obviously, it will move from this point to this point, it is moving from this point to this point, then it is moving to this point. But because there is diffusion also, is not moving with the same peak and not the same spread, it is also spreading and the peak is maybe going down a bit. Okay. So, and now because I am adding not only dispersion, but not only diffusion, that is in the molecular scale, but dispersion which is larger scale of mixing. So, therefore, the peak will go down faster. Okay. So, the spread will be more. With diffusion maybe not that much, only fraction of it. Now, generally I will tell you the molecular diffusion is very, very negligible most of the time. So, in general most cases, but it is the dispersion part which comes from the heterogeneity and the tortuosity, everything, that is additional mixing process, that is much more important and much more pronounced compared to the molecular diffusion. Molecular diffusion is almost negligible, especially if the velocity is slightly high. Okay. So, that is very important. So, now if I combine this thing, there is advection, so it is moving from here to here, but also there is a mixing, more mixing, and you can see that it has spread for a larger area, over a larger area, but the peak has come down to maybe 50 or 60 over here. Okay. So, that is the effect. Oh, time. Oh, that see, because it is at time t1 it is here. So, at time 2 because it has got advection also, because the one I showed before it there is no advection. So, obviously, I showed at the same time at x1, but different location same location, okay, at different times, but here at time. So, you are introducing maybe in a groundwater system, you are introducing, there is a pulse, you are just dropping instantaneously some pollutant over here. After some time, say this is as T1. So, if there is only advection, it will go, the same thing will go to T2. Okay. It will moving over here at T3 because there is advection, okay, like this. So, time is, but then it is also moving from x1 to x2 at x3 at different times, because you is moving over here, and also after some time, after sometimes going here, after sometimes going here, after sometimes going here. So, that is T1, T2, T3. Okay. As you can see, it is moving over here, but as you can see, as it is moving, so also initially the pulse was like this, but now it is spread over a large area and the peak is only this much. Okay. That is what it says. So, T1, T2, T3 in this case, or T4 is the time, distance is along the flow direction. Okay. Is that okay? Okay. So, now how to model that dispersion part or diffusion part? I do not want to go too much into the details, because that will be too, I do not think you will appreciate it, or you want to hear that also, but at least you should get the idea that where it is coming from. So, what happens is that suppose you take some kind of cylinder or something, maybe this, and there is some kind of membrane. Okay. So, it can pass, the water can pass through it, but here you put some solutions, maybe saline solution, okay, high concentration of sodium chloride is there, okay, and it is all fresh water, and there is some kind of membrane is there which allows the water to pass through it, but it is all saline water here and fresh water here. Put in a beaker or something like that. Okay. It is a beaker, and this. After some time, you will see that concentration of salt over here has increased. I mean, it is no longer 0, but it is increasing. Okay. And as a result also, or as a fact, the concentration of salt will over here will be decreasing. Okay. So, that is, so it is passing through this so called barrier, it is all salt water and fresh water, but because the concentration was less over here and more over here. So, there is a concentration gradient between this point and this point. There will be move of the of the species or whatever the pollutant or contaminant of the species from this point to this point, and how much and how it will be, or how fast it will be moving from this point to this point and this part was defined by what is known by Fick's law. Those who have read physical chemistry, I think some of you might have come across Fick's law. I do not know if anybody is taught, because our time of course is taught in the first year. So, physical chemistry first year when I was a student at IIT Kharagpur here, but I do not know about you, because in class 12 is a different issue. So, I do not know where it is. Fick's law is something which is which defines, or actually is based on which the diffusion process can be modeled, is very conceptually it is very simple. I just for 1 minute I will explain to you that it also comes from Brownian motion and random motion of the molecules. Okay. What happens, these all fresh water. So, there is more only water particles here, there is water particles and maybe salt particles here, though it is dissolved, but this dissolved particles are there here. So, more of the molecules or salt molecules are here, no, none of them are here. So, if there is random motion, so what will happen, some of these are moving this way, some of them moving this way, some of these are moving this way. The moment some of the salt particles are moving this way, okay, its chances that more of the salt particles are here, none of them here. So, more will be moving into this direction. Okay. So, therefore, the salt, you understand what I am saying, here there is lots of salt, there is no salt. So, if you consider the maybe salt molecules or something, or and water molecules. So, both of them are moving this way and that way purely randomly, but because more salt particles are there or salt molecules are there. So, when they are moving randomly this way that way, obviously, it will try to equate, because might be more of them, the salt will be moving here and less nothing is moving from here to here. Okay, that is initially. So, ultimately what will happen, after some time will equilibrium, and then everywhere it will be the same concentration. So, really the idea of Fick's law came from this Brownian motion, again the molecular scale movement of the particles. So, if you just take a beaker, keep the salt, and this has some membrane like through which the water can pass, you put it here, and after one day you look at it, everything has become the same concentration. Why? Because there is no movement, no advection, but there is a diffusion. Okay, that is the diffusion process. And what Fick's law says that the flux, the pollutant flux or contaminant flux of the species, how it will moving, that is given by say Jx or something, is proportional to the concentration gradient, that is del dc by dx. Say here, because the concentration is very high, it is almost 0, the concentration gradient is very high. So, lot of movement of this will be there in this direction, because salt concentration almost 0 here is high, the gradient is very high. So, the flux will be quite high, because it is proportional to this gradient del c by del x, and gradient is very high initially. Okay. When they become equal, the gradient is almost 0, the same. So, that is Fick's law. Of course, he just observed that it is proportional to the concentration gradient, and of course, the more area you have, that will depend upon the cross section area through its path, it will also be proportional to that, you have multiplied by this A. Okay. So, but then it is proportional, again the same concept, just like Darcy's law. You see, if it is proportional to the flux of the pollutant or concentration or any chemical species will depend upon the concentration gradient, of course, at the cross section area through which it is passing. So, if it is small cross section area, nothing can pass, large area it can pass. So, therefore, so if it is proportional, so it should be equal to some constant of proportionality into this del c by del x into A, and this is the diffusion coefficient. Okay. So, this is the diffusion coefficient. So, now the flux that is taking place of the contaminant due to the diffusion process is defined by this equation, which comes from Fick's law. It is also known as Fick's first law. Okay. There is a second law, and I can go to, but Fick's law. So, now it says the diffusion is very important, and if the diffusion coefficient is high, of course, there will be more flux. Okay. If less, it will less flux. So, we can, by analogy, you can also go to this, I can go to the groundwater flow system, I can use the Fick's law. I said the flux. So, first I have found the flux which is coming from the advection process. Now, I can add or subtract whatever it is, you have to be careful over this, because now for advection the particles just coming from here to here to moving. Okay. But now, by diffusion it is actually more spreading. So, actually you are losing, might be losing some of the particles. So, you have to be careful of it. So, but ultimately you are looking at the mass balance, because by diffusion spreading, so concentration will actually decrease. Okay. By advection is just going from here to here, the concentration not changing. Okay. But here is like, but the moment you are mixing it, the concentration is decreasing. So, by diffusion actually it will result in the decrease in the concentration. Okay. And I can use the Fick's law and say, okay, this how much that concentration will effectively depend upon this concentration gradient, and of course, it will depend upon the diffusion coefficient. Okay. So, that gives you enough, of course, this is the flux, and I will not don't want to, the areal mass flux rate is given. There is another definition is Fx, which is areal, I think areal mass flux rest actually is aerial mass flux and its rate, okay, per unit time, that is given by Jx by A. If you just take out this A per unit area, that is more normalized, become this thing, okay. This x is for the x direction. So now it's very interesting. So I have introduced the diffusion coefficient. So now del C by del T I can come up again from the mass, mass balance equation, something like advection. I can come up with an equation which is, so del C by del T due to diffusion will be given by minus sign again, that take care of, that cannot be negative. So del square C by del x square. So that is what it is. So by using this, the mass flux is given by this one. So this is diffusion coefficient del C by del x, and I don't want to go into derivation, but it can be derived. Actually, it's very easy. Again, taking control volume, find out what is coming in out, and then you can get this. So you can get del C by del T, that is changing constant time due to, now it is only by diffusion. That is actually d into del square C by del, the second order derivative del x square, okay, is different from the advection equation. Okay. So now I have to add the effect of advection and diffusion. Now what happens? So and then I should get the transport equation together. This is just because the mass flux, again, it's adding the effect, it's additive in some ways. I can superimpose one and the other, not really superimpose, but something similar. But another question comes is, what is dispersion? This is okay, I can follow Fick's law and look at the model the diffusion process, but what happens to dispersion? As I said, dispersion is a more significant mixing process as far as pollutant or chemical species transport is concerned. There is, even for surface water, what we sometimes do is, we can say, so surface water has got both diffusion and then maybe turbulent diffusion, which is dispersion, which is mechanical mixing. So here also you have dispersion, which is something similar to mechanical mixing, not really, but I can say it's analogous. So what has been proposed, that we can use the Fick's law still, but we play with the diffusion coefficient. So because the effect of the diffusion process is much less significant, it's much smaller. So the diffusion coefficient, if it represents molecular diffusion only, is very small, okay, very small. But if I can superimpose on it the effect of this mechanical mixing, tortuosity, the heterogeneity, because actually the water particle is not moving like this, is moving like this. So as it is, when it's moving, it's mixing up. So that is taken care of by this. Still the diffusion coefficient, but I call it actually dispersion coefficient. I can say, okay, it's actually dispersion plus diffusion. There's two coefficients I can separate out. Or I can say, what is more important is the dispersion coefficient, which is a much larger value, which has got few orders of magnitude larger than the diffusion coefficient. Okay, so it's a very similar analogous process. Okay, so if that happens, then I can say, okay, now I have included the dispersion, diffusion, everything. So now I am not going. Maybe I don't know whether I have this mass balance condition or not. I can actually derive all this thing. I didn't want to waste too much of time deriving everything, because I can again consider control volume and say, okay, this is the process, first one, second one, look at the mass balance, and all these equations could be derived. Okay, so that's not just take it from me. I'm just giving you the concept. So I can actually include the diffusion coefficient to include both the dispersion and the diffusion process, because diffusion will be generally negligible. The velocity is not very small, the molecular diffusion will be almost negligible, okay, comparatively. So therefore I can use this equation to model dispersion. But I am saying again also, dispersion is, you cannot go in the field and measure what is dispersion coefficient. It will depend upon the degree, the scale of your model. What is the size of the study area and how you are discretizing it, and discretization will determine what is the dispersion coefficient. Okay, That is very important. So, you cannot really go in the field and measure it. Some people say it is a first factor to get the correct answer. Some people say you can introduce numerical dispersion instead of doing all these things. That is also true to some extent, but I think it has got a physical significance, that the tortuosity and other things. And the more, if you can look at the structure with an X-ray or something and very macroscopically, you can say, okay, this one might have a larger dispersion coefficient. But generally, it is a factor which depends upon the discretization scale, that is what is the size of you. Now, one thing I want to say, that when I am talking about finite difference, that I am really, you have a study area like this, I am dividing into number of grids, the size depends on a lot of things, and I will probably mention something, and then I can approximate this as some grids. And if you have very irregular scale, then it might not be using this grids which are almost square or rectangular, most of them square, but it can be rectangular also, may not be very suitable. So, you might have to go to what is called finite element methods. Okay. The idea is very simple. It ultimately it also converts all the differential equations into algebraic equations simultaneous, but it depends on stiffness matrix and nothing much more complicated in a way, and it does not use only squares, it uses triangular elements or what is called finite elements like this, and it might be of different sizes. If you are pumping at some certain area, it will. So, these are called finite element mesh. Okay. Element mesh, and it will generate, you need to generate the mesh first and then solve it. You cannot, but if in finite difference, this is the finite difference method, finite difference methods, where you divide this, you actually superimpose the grid system on it, and then you will know exactly where is the node of the grid here and here, you can actually fix those coordinates. But if you generate a mesh like this, so for finite element, basically it is a collection of triangular or tetrahedron, all kinds of elements over here, and if you are pumping from here, this is more nonlinear, it might have smaller elements here, maybe it is larger element, all kinds of things are possible. And also the GMS that I was talking about, one of the good thing about the GMS package, the ground remodeling system, that they have one program which is explicitly used for generation of the finite element mesh. So, you do not have to generate the mesh yourself, you define the problem, it will. And even if what we have done it, we are using some other program also, but the finite element mesh I actually generate using the, I think it is called TIN, also the program is called TIN, which is one of the programs or sub packages available in GMS, and that comes up with that. I don't know whether it's TIN or most probably it is, I don't remember exactly. So, it can generate the finite element mesh, and then you can solve the problem. Okay. So, it's irregular boundary, very sometimes for accuracy you go for finite element, but idea is simple, you are converting the partial differential equations into algebraic equations. Yes, just asking something.
Sir, is there any thumb rule for using finite difference and finite element?
No, but generally people say finite element is slightly more accurate, but it's complicated, because I don't know whether mesh generation is correct or not. And if you suppose you have 3 pumping locations, but suddenly you want to add one more, then ideally you should change the whole finite element mesh. If you do not do it, probably you are sacrificing in accuracy. So, those things has to be remembered. The biggest problem I have with finite element is that there are some programs like this FM water in GMS, which is the saltwater intuition model, I think uses finite element. But suppose I want to fix the monitoring locations, okay. So, I know the coordinates exactly. So, if it is, so I will get the values of the maybe concentrations at those points if I use finite different grids, because the grid points or the nodes of the grids are actually up to me to decide and fix it. So, I can actually get the values of concentration at those grid points, here, here, here. But when it is finite element, it generates its own mesh, and I want the concentration at this point, but it is not at a node. So, I have to interpolate, all kinds of things have to be done. So, sometimes it's complicated, but in general if you ask me, maybe finite element is slightly more accurate, but not always. Okay. But if you want to go choose,
Which cases we should go for finite difference, and in which cases?
As I said, if it is very irregular boundary, and also sometimes layers are, if you have very nice layers, one layers, 2 layers, horizontal layers, you probably go for finite difference. Okay. Because grids are also in the z direction, but one is I have seen recently we were trying some problems, we found out that if the layers are not like this, 1 layer, 2 layers, but it is layers are like this and like this, or some, so all kinds of layers are the intersecting, finite difference even does not give the converge, the solution does not converge. So, finite element might be required. So, if you can get, but it also depends on what type of accuracy you are getting, whether you are getting a stable solution or not. And another issue is that you cannot fix the size of the grids yourself, because you might say, okay, I have a 10 kilometer by 10 kilometer study area. So, I will assume maybe 100 meters by 100 meters grid. Now, who says that is acceptable? Because when you use 100 meters by 100 meters, you are getting some head values. If you reduce that to 50 meters by 50 meters, you are getting different head values. So, that means your grid, your solutions depend upon grid size. That means your solution may or may not be correct. So, if it changes with the grid size, that means your solution has very little meaning, isn't it? So, you have to see, okay, if you make it smaller, is it changing? If it's changing by how, if it's changing, if you make it 100 meters by 100 meters to 50 meters by 50 meters, 50 meters by 50 meters, if it's only changing by half a percentage point, 1% or something, maybe you don't bother, you said okay. But you have to do that test and say, okay, for the example problem you're trying, more or less the 100 meters is acceptable or 50 meters acceptable, okay. But if you're changing with the grid size, then your results has no meaning. So, what will calibrate, what will validate, you cannot do anything.
For the same aspect ratio, finite element gives more accurate result.
In general, but there are issues like that, So, like there are certain capabilities of finite element that it might have finer mesh near wherever non-linearity is more, and to do that with the finite, it is possible to do that with finite difference method. You have finer grid over here, it can be done. I think Modflow also has that option, but it's slightly more difficult, okay, accuracy wise. But then if you are getting more or less convergence with finite element, finite difference, there is no issue. But if you want to choose, maybe finite element may be the first choice, but it's sometimes complicated, okay. But if you have a program which does all these things and generates the mesh, so who cares? So you can use that. Okay. But one problem, because especially we had, is that when you want to fix the monitoring points or where you want to values, I cannot fix that in finite element method, because the meshes are generated by itself. I don't have a control where the nodes are. In finite difference method, I have the control where the mesh is, okay. So I can control where I get the output values, okay. Otherwise, I have to do interpolation. Another issue also, I think, who was asking? Yes, I think you were asking that, that there are even GMS and many other times in groundwater systems, generally the data is very sparse. You have to go for interpolation and extrapolation, all these things, and estimation, spatial extrapolation to, otherwise you cannot even start running the model. So then you have to use statistical interpolation and estimations, and those options are there. You can use what is known as kriging. Kriging is a is a geostatistical procedure, or you have some many. So average, you take the spatial average, weighted spatial average. You can choose the method, and sometimes you have only few data. Don't go for kriging, because it depends on a lot of other factors. You might give all wrong results. Okay, so how you interpolate the data statistically. So those options are there, but you have to be careful what. So that those things are necessary for creating the input files also. So you have five values of heads that you cannot run the model. You need the head at every node. So that is also. So then if you only have 5, you have to extrapolate it. And if you think that is here value is given as 100, and this is an example I will discuss. We always face some of my students. Here a value is 100, here is 99, and this is 85, 86, and 40. Say 95 or something. Okay, 5 values are given. Now you want the values at every grid. So they use some kind of statistical interpolation, and then what it does is that is assuming it is 0 here, 0 here, 0 here, and then this is 100, or this is 80, this is 60, and all kinds of things, because assuming all zeros. Because if you assume all the zeros and if you take the average, spatial average, then it come up with some very absurd results. Okay, because these are not 0, only that you don't know the values. So if you think it's 0 and then finding the average value and trying to assign it, absolutely your model has no meaning. Okay. So those things you have to be careful. So grid independence test is very important. I cannot emphasize it more. Independence test. So whenever you use a numerical model, you have to show by something like the sensitivity analysis that if you change the grid size or something, your results are not changing. Okay. But it is the smaller you get to make this grids, so more accurate it is. But once I think I'll show an example. But also the solution starts oscillating. If it starts oscillating, because it's too small, it's no longer accurate. So you have to stop somewhere. Okay. But suppose from 50 meters per to 50 meters and maybe 25 meters in 25 meters grid, this values are almost similar. So you can plot it, and they are almost similar values, and you can see, okay, why not go for 50 by 50, because of computation is that efficient. Okay. But if you are getting a lot of difference between 50 and 25, you have to see where you should, whether you stop at 40 or 20 or even go below 25. Okay. So otherwise, unless you do that, your model is not a model. Okay. Grid independence test is very important. Okay. And without that, if you do calibration, what it means is nothing. You are trying to fit the historical data, but it is not even giving the right results. Okay. So stable solutions means it starts oscillating. Okay. From one iteration, because how this numerical models are solved, it's iterates between first one iteration, second iteration, third iterations, where it is inverting the model, inverting the matrix or something, and sometimes the matrix becomes very sparse. You get a lot of zero values. It becomes indeterminate, and you get all wrong solutions. Then what happens? One solution, maybe the concentration of your head is 20 meters. Next one you'll see it is suddenly 15 meters, and it's 14 meters, then 25 meters. So one iteration to another, there's a lot of change. That means not moving in this direction that it's going like this, but it is going like this. So that is oscillating. So if I stop over here, you get this value. If you stop over here, you get this value. So this
is the actual idealistic situation, because groundwater table data, if we observe that there is some fluctuation during monsoon and non-monsoon period. So normally we sine curve like this data if we see.
Yes.
So if my model runs in this fashion, that does give me some interest that yes, my model is showing the trend instead of like this simple line. So which one will be the realistic look for identifying?
No, if you have a trend that is the true trend, it should produce that trend. I'm not saying that you cannot have at a cell different values with different times. Maybe you have 4 seasonal values, so maybe it should give 4 values. But then in one same season is giving one iteration is giving 15, and next iteration is giving 25, and again is coming back to 10. So then that's oscillating. So that is not accurate. I mean, that means there's some problem, numerical problem. But if you say what you are saying is seasonal trend is there, it might be a groundwater table might follow a sine curve, or sometimes you use the boundary condition like that also, because the reverse stage also becomes like a sine curve. So but then it should reproduce that trend. But what happens is that in one iteration is giving value here, and another iteration giving value here, so then it becomes problematic. So that is oscillation. Okay. I think I have an example I'll show. So this more or less, I think I'll talk about some of the mathematical models in the next hour. So basically a bit, I'll go slightly deeper into it. I will talk about some of the study areas that we have actually modeled and something, but maybe it will be in the last 2 days or something. So I'll start doing that. But what I'm discussing also is relevant. You can ask any questions, I can discuss it. But my point is that unless you understand at least not the equations, everything, but the basics, then whatever I say afterwards, it will not be very useful. Okay. You will not understand what. So that's my idea. So basic is very important. Okay. Any other question? Okay, then let's break. We'll break for I think 15 minutes. No, is Oh, you were the one who was asking about Kriging average, no? That weighted average method? No, you asked. No, someone asked. These are all part of GMS. Oh, you are not okay. Okay.
We know now basics of the softwares, what we use, basic terms. Then only we can understand its later part. Otherwise, we can't understand.
Yeah, one thing I didn't want to discuss the software too much, because then we're deviating from the contents. But I'll discuss a bit. But you understand that it is if I discuss too much about the software, then it becomes a different kind of presentation.
They have little modeling tools. Sessions for modeling.
Okay. Okay. Thank you. So, one thing of course, we have now discussed about the I will come back to that transport process a bit more, because I have not introduced till now the reaction part, but again, as I said, I can first look at the advection, then I look at the advection part dispersion or diffusion, and I can similarly, by using the mass balance conditions, I can look at reaction, because when you have reaction, so basically two species react and probably then create another third species, the concentration is either of the species will actually decrease. So, there is a lot of loss of mass. Okay. So, this can be done, and sorption, as I said, also there is some of the particles will be taken out of the solution and adheres to the solid matrix, and there that is also loss of mass that can be done. Okay. I will discuss that a bit, but before that I also want to discuss one more thing about the flow equation, and which I have not done, and probably none of you have asked me that. Of course, this is the three dimensional flow equation. Okay. So, that is very easy. So, it is instead of 1 I have kx, kxx, kxy, kxz. So, 3 values in 3 directions. So, it is anisotropic medium. So, hydraulic conductivity has 3 different values. By the way, I will also strictly speaking, this k is actually called hydraulic conductivity tensor. So, which is basically 3 by 3 matrix. Okay. So, 1 2 3 3 3. So, we have kxx, kxy, kxz or something like that, all 9 values. So, though I am talking about anisotropic and k equal to 3 values, maybe kx, ky, kz, what it means is that, so it is a tensor, that is like a matrix. Okay, 3 by 3 matrix, 9 elements. So, when we assume, and this just for your information I will just mention this, that one of the directions coincide with the principal directions, say x, and that is the direction where probably the hydraulic conductivity or what is the parameter value is maximum. So, that is, I suppose I know, and it is not that always I will know, but I for some reason or I can assume that this is the direction in which hydraulic conductivity is the maximum out of all the directions. So, that can be considered as the principal direction. Okay. And if you can find the principal direction, any direction which is orthogonal to it, that is 90 degree twist, that if this is my x, this is my y, this is my z. So, then I can actually, this hydraulic conductivity tensors actually reduces to a vector. So, this becomes actually like kxx, kxy, kxz. Okay. Only 3 values and all these values have become 0. Okay. And or kxx, which I can tell actually is the kx, this is equal to ky, kz. Okay. So, the underlying assumption, and it might be just for your information, is that I know the principal direction, and then this the whole tensor of hydraulic conductivity becomes a vector with 3 diagonal elements. For anisotropic conditions, this kx and ky, kz, which is different. For isotropic condition, of course, that is the same in all directions. It will be kx equal to kx equal to kx, all kx. Okay, that is k, only one value. So, actually, it is a vector, just for information. So, here that is why you will see that it is kxs, kxy, yy, kzz. Oh, this kxy, kyy, kzz, I wrote it wrong. Okay, this kxx, kxy, see yy, kz. So, these are the values. Let me write it clearly. Kxx, diagonal elements are kyy, and the other one is kzz. Okay, and I assume all of these are 0, all rest of it 0, and these values are this. Okay, diagonal matrix, which is a vector. Anyways, I can actually expand that flow equation. See, the same equation, if you can see on the right hand side, of course, transient, the storage specific storage SS is there, which is more generic for all systems, confined or unconfined, and del H by del T is there. So, it is of course transient, but I have introduced one more term, that is plus minus W. Okay. And W is the volumetric flux per unit volume representing source and or sinks, and this is very important. W is the volumetric flux. Do not get scared by the word, but it's what it says is that the flux is like like flux is coming, the mass flux or volume flux, so whatever it is. So, there is a rate that is coming in. Okay, the rate at which coming in is, that is time varying amount, there is a flux. By volumetric flux, if you are pumping something, there is a withdrawing. So, you are withdrawing that water. So, I have not introduced withdrawal or pumping so long, because that there is no so one is sink term. Sink term means if you are just taking out the water, pumping, it is like a sink, you are taking out of the system, it is gone, mass from the mass balance. So that is sometimes called a sink. It is a sink. Or source is if you are recharging. So if you are recharging, it becomes actually a source, because source of water. So now I am introducing, and this even because it is all mass balance, so everything is based on mass balance. I can also add to that. I mean, there is some derivation. I am not going into just, you can believe this one. So this is another term which is source and sink term, which represents the pumping or recharge. So when you are considering the control volume, we did not consider anything which is coming in out as source or sink. So pumping or recharge was not coming in, but I can introduce that into the equation, and that is W. And W is the volumetric flux rate to represent source and sink terms. I have not given the sign for most of the times. Actually, a positive value will put recharge and negative value means pumping. Okay, but it depends upon different programs and different software will also use different signs conventions. They will tell you exactly which one is positive and negative. Okay, so one is the negative of the other. Recharge is the negative of pumping, or pumping the negative of recharge. Recharge is coming in. So therefore now this flow equation is more complete. It is transient. It is anisotropic, and also I have introduced the source and sink terms. That means if you have a study area, you define everything. Also there are some locations where you are pumping or recharging. So these are the some maybe pumping P1, P2, P3, and maybe you are recharging something. So that is the negative of pumping. So that is also possible. So all this can be included in the equation and then solved. Okay. So therefore when you write in the finite element form, of course what will happen? Suppose a finite difference form, maybe that means every node you can say, okay, you can now give not only say what is the k value, the hydraulic conductivity value, maybe kxx or kx, I will just put a kx, ky, kz, that will be one in the input, and at this point it might be another value. So at point value 0.1 I said k2x, k2y, k2z, that means you can put different values of k at different in different directions. So it is anisotropic, and because you can also put in it is very easy to put different values at different locations. That means you can use a heterogeneous system by giving different values of this kx and k at this point, this point, this point. You can easily introduce the heterogeneity in the system. It may not be the same. It need not be the same. It is very easy to do that. Okay. So some people say, is it your system is heterogeneous? I said yes, it is very easy because you can give different values of k at different, and you can still solve it. Okay. All you need is to specify these values, and of course it might be anisotropic, different directions, but also every node you might be giving the information whether there is a pumping or recharge. That means if there is a pumping, so maybe there is a withdrawal, is some negative value of the sink, that is a sink term, or maybe here is a source term, maybe recharge, here is the pumping, or here is the pumping, and here is the recharge. So all these things can be, so you can, or it is 0, everything is 0. So now you can, so now here modeling, of course you need to give all these values. You need to give the boundary conditions, maybe head, whether it's known head or flux, or you say it's no flux, so that means hydraulic conductivity is 0, nothing goes there across. All kinds of things can given. You can give all the values of the parameters. You can give porosity also, which might vary from one point to another, so that can be heterogeneous also. And also you can give the recharge values or pumping values at different locations. Now you can and another point is that even if it is 3-dimensional, so maybe it is like, maybe it's not, I am not drawing it properly, but so also you can give the values at first layer, second layer, third layer. So you can model a 3-dimensional system where you can give all these values: pumping, recharge, hydraulic conductivity, different direction, different values, porosity, and boundary conditions. Okay, all these things. So what do you get it? Because dH by dt. So what is on the right hand side is dH by dt. Okay. So what you are getting is dH by dt, that is h is equal to dependent variables really. X, y, z, everything is, t is independent, so you control it. What you get as a solution is h, and you get h as a function x, y, z, and t. That means you get the hydraulic head distribution at different locations at different time, including pumping, recharge, everything can be now included. Okay. But it can be solved only if you are correctly given the boundary condition, initial condition. Initial condition is also necessary. At every point, maybe you give to h at t equal to 0, maybe you have to give not only at this point, even if you have 3 layers, at every point in the 3 layers. Okay. Or 3 layers might be divided into smaller grids also, so every point you have to give. Okay. That is very important. initial condition, because you start from here, then you can march here, and then you can march here, you can march here. If you cannot, don't give the values here, you cannot march here. Okay, so because marching the solution from here to here. So this is very important. So now you have a complete. So now if you give me the study area, and I can estimate what might be the boundary condition here, or there's a river going, I can say, okay, maybe the river stage does not change, or I can use some kind of average value for the whole year, or maybe 2 seasons, 2 different values, some average value. I can say, okay, these are all constant heads, I know, so I can give the constant conditions. If I say nothing is coming out because it's the aquifer is divided over here, maybe it's all 0 flux, okay, k equal to 0. If I put k equal to 0, it automatically becomes 0 flux, nothing goes inside, okay. It acts as impermeable, nothing else, like a stone, okay, like a rock or something, so that kind of thing. So I can give all these things and then divide into number of finite different grids, and it can be not only 1 layer but 2 layers, 3 layers. It can be, you know, like this, and layers may not be like this, as I think you were just now asking. We are trying to do this, but we are having a lot of problems. So layers may not be like this. No, these are of course the plan view in this direction. This first layer, layer 1, layer 2, layer 3, and sometimes it may not be like this. It might be like this. Okay, so one is intersecting. Then getting solutions. At least one case we are having lots of problems when they are intersecting layers. Okay, so we did not get a solution, but not for mod flow. It's for another saltwater intuition model, FEM water. Okay, so these things are possible, but theoretical everything. Now we have everything. So what is the solution? H as a function x, y, z, and t. So every layer, every grid points, whatever it is, now as a solution, you should be able to find out what is the resulting H at a given location in the z direction or x and y direction plus z directions at different layers, So this can be also divided into number of grids. So all these things are possible, and also different times. Okay, so that means you know the system. So at a given time, if you know the values of H here and here, you can come up with nice contours, how it looks like. Maybe it's moving like this, and you know how the contour looks like, because you know the H as a function of x, y, z, and t at every t. Okay, so you can come up with the contours, and then you can find out what is the direction of velocity, what is the gradient. Everything is possible, but most importantly, once you solve this, mostly by numerical methods, what you get as a solution is the hydraulic head distributions at every location in the study area at every time. So that's it. So I have everything to solve for the model. Any question about that? Because
very basic question, sir. From where you know H, you know all the things. So then if you know H, then I can find hydraulic distribution of the study area.
head distribution, yes, hydraulic head distribution.
So from where we find H firstly?
No, okay. Let me say. Is it are you saying what I am saying is that you can find H, or you are saying you need H? Which one you are saying?
Sir, I need H. Firstly, we find H. Then after that, we find the distribution.
Yeah. So this is part of the solution. Okay. This comes from the solution of because once you solve, yeah, it's the mathematics you solve for this, and you get at every location at time you get this value. But what I am saying you need to know is if t is a parameter, that means is transient case. So this head or whatever it is, or concentration, anything which varies with time, then you have to give what is the initial solution. Okay, because one thing is, if you are suppose it's one dimensional, so you need to start from many initial point and go from here to here to here to here. Unless you know the values over here, you cannot go here, you cannot go here. So that's the initial value. Yeah, I am coming to that. That is one thing. And in the x direction, suppose the one dimension, also you need to make the boundary at this time starting point, and then you have to give all these values. Otherwise, you will have infinite solutions. All of them might satisfy, but none of them represents what it is in system. So that is one basic requirement. But your question is, where do I get this? Is it?
First solution.
Not only first solution, because you have to specify this initial condition, boundary conditions. If you don't know it, you cannot model it. You have to get it from the field.
We go in the field and find the
Yeah, like I mean, it's not that every time you have to know the field. If it's a real system, you want to model it. So unless you know what situation you are starting from, how can you solve?
from history.
Yeah, history means suppose you want to find out what will happen in 2017. Okay, and you are starting from 2015. So if you don't know what is the status as 2015, how can you predict what is going to happen in 2017? So you have to know this. If you want to say it is varying with time, it's not steady state, it from 16 will be different and 17 will be different, 18 will be different, you want to predict it. So, you should know when it's starting from, is 16 or 15 or 14, where it is starting from, okay, and then only you can predict in the future.
This modeling is done only for the future perspective.
I don't know whether it's only for future prospecting, because this is a simulation model, okay. So, what I am saying is that if you know the initial condition, if you know the boundary conditions, you should be able to predict how the system behaves, okay. Whether there is a prediction or you are simulating, if you do that, I will tell you one thing, and this is very important. One is simulation model. I do not want to complicate, but simulation and optimization model, and I will just in simulation model, it says what if, okay. The answer, what it answers is what if I do this, what will happen, if this is done, what will be the effect. So, in that sense it is a prediction, but it is also simulating what will be reaction of the system to any stress or anything you want to do. You know you are pumping like this, and what will happen if this same pumping continues. But if you ask, if you increase the pumping by twice, what will happen in 2 years? Will the water table go down or the headache go down, like that. So, in a way predicting, but also simulating how the system is not a prediction in the sense it may not be the actual situation. You are trying to just think of some hypothetical scenarios and see how it will behave, okay. So, that is not really a prediction, but you are actually simulating what might happen. So, you are answering the question of what if, what will happen if I do this, or if this happens, this is the stress. So, simulation is what if, and optimization. So, this is called what is called descriptive models. It describes how the system will behave. Sometimes in the other mode, when optimization, I have not come to that, it might answer is what is to be done. If you want to achieve this, what is the best solution, that will be answered by optimization. So, that is a decision model, and this is a what if model in a descriptive model, and that is a prescriptive model that prescribed what is to be done. So, that is not really a predictive model, it says what needs to be done, okay. So, but here what if means, and you are saying, okay, I don't, there maybe never I will increase the pumping by two times, but if I do that, or somebody starts, everyone starts pumping twice for irrigation. So, what will happen in 2 years? So, that is not really a prediction, but you are saying to what if and how the system will respond. So, that is simulation. But to that, if you just cannot say, I do not know the situation now, but what is happening in 2017 or 18, but no, you cannot do that. You have to say, I know the situation in 2015, and from here I start this pumping rate, and then what will be the effect, okay. Otherwise, it has no meaning.
So, sir, for forward modeling, we need simulation, and inverse modeling, we need.
Yeah, for optimization, generally inverse modeling. What I try, not always, there is a planning model, management model, where you tell how to increase the maximize the pumping and what type of distribution needs. So, it will prescribe what kind of pumping is possible to maximize the total pumping from the area, okay. No, optimization you can, it will give you an answer in a one shot. If you say, I want to find out how much maximum I can pump, okay, and the concentrations of pollutants should not increase beyond this limit. So, you try to find a solution, but by optimization, I will come to that, and that is what source identification, maybe the inverse model said, that is inverse model you are trying to solve in the inverse model. But you can get the same answer from simulation model. You can say, if I pump this much, what will happen? If what is pump this much, what will happen? If you could simulate exhaustively, by exhaustive, I think all possibilities are taken care of. This is of course infinite in number, but suppose the exhaustive search, then it will give you the same answer that you get from the optimization. Optimization maybe give you the solution in one shot, that this is to be done, this is prescribed, and I will come to that. And simulation, you might say, you can't think of 10,000 scenarios, okay, so if I do this, what will happen, this, and then you say, okay, this is the best one, and probably, and that might be very close or even something very similar to the optimization solution. But then, because you are asking what if this is done, what will be the response, on what will be effect, what will be this thing. But optimization said, okay, this is what so it will prescribe what is the best solution, this will describe what is the effect. So, that is the difference, okay. So, simulation of course, but simulation without giving the initial conditions and other things, boundary conditions, you are not defining the system. So, it is it is not something magic or something is not God or something, it is a mathematical tool. So, it should know. So, where it is like if you are telling some blind person to go up the stairs, you have to say where is the stair starting and what is the height of the stairs, all if you do not say, nobody can, that kind of thing. So, that is exactly. So, computers are something like that, you have to give them the instruction exactly, otherwise it did not know, it does not have intuition. So, that is yours, okay. but you have to give the data, otherwise your simulation will not have any meaning. Is that clear? Okay. Oh, where was the simulation optimization? Okay. So now I have completed actually the flow model and then modeling, and if you look at mod flow, and they will be using this kind of things, everything. So they will be solving this system equation, but you don't have to solve it; it will solve itself. Okay. By the way, I was talking about GMS and other things. I think, as someone asked me also, that I think mod flow and MT3DMS are public domain software if you want to use separately, so you might be able to use it. But if you go to GMS, there are very good tutorials and other things you can start from the beginning. So it is not easy; it takes time to learn, and you have to look at the example problem, see what is the what is the input file that has been created, and then what the input file means, every variable means, and what is the study area, what is the assumption, and how that has been put in the input file. And if you go back and forth, I think you can learn. Okay, that's not difficult. So that is. But these are also public domain softwares. I think USGS has developed it. I don't know which version, but some of them are, even the manual is available on the internet. So if you want to use that, you can try that. And mod flow can take care of all these things, river and aquifer interaction, drainage, as I say, because some of these recharge problems, I think, yes, you were asking, drainage and things where you try to recharge through the trenches and drains and all these things, and those things. And it can also take care of the interaction between the unsaturated zone and saturated zone, because as the water table moves, this might, if it goes down, so this was saturated, but it will become unsaturated. So that interaction of this has to be taken care of. So that mod flow can do all these things. So I don't want to go, but these are. So you don't have to solve the equations yourself, but you should know what you are solving. Okay. So this is the equation, and again, storage coefficient x, y, z. So what you need to understand is that you need all these initial conditions, boundary conditions, define the problem. And also you need to know the source and sink terms, so that you know how the system behaves if you impose some kind of stress. Stress might be in terms of putting some concentrations or pollutants with some concentration, or pumping or recharging. That is also you are stressing the system. So how it responds to stress, that is simulation. Okay, basically, so it describes how it. So basically, you are saying, okay, I don't have to go to the field and say what will happen and measure it, but if I have the model correct, it's calibrated and everything, so I should be able to predict how it will behave. Okay, and by prediction, again, I am not saying predict in the sense I am saying that what will be the response. Okay. Prediction means you know the scenario and this is exactly what is going to happen, and then you check whether that happens or not. So slightly like forecasting and prediction, there is some difference. Okay. Okay. Now also, I'll not go too far into it because we are looking at the transport model, and I'll basically say, see, del C by del T, we looked at the first part we looked at was the advection part, and if you look at the advection part, is the second term on the right hand side. If you look at the, I don't want this probably too small, but if you can look at it, is the second part in the right hand side. So that is the advection term. So it was, we are looking at del C by del T again, change of concentration with respect to time, and that is what we need, and C becomes a function of x, y, z, and t. So that is the solution will be nothing but the concentration at different points. Okay. So you can just like head, I can now solve for concentration if you are solving the transport equation, and transport equation has got these parts. Okay. One is the advection part. If you remember that u, I think you, instead of v or u or something like that, this is very similar equation. That if you remember the advection part, that is advection part is contained in the second term. And the dispersion part is actually a second order derivative. If you remember, del square C by del x square, and the coefficient is the what we call, it's a bigger name, but it's the hydrodynamic dispersion coefficient. It's a tensor. Of course, it can be a tensor like it's a matrix, but it can be a vector also. But let's say there's a parameter, so that is the hydraulic. That is the dispersion tensor, sometimes called dispersion coefficient or something like that. But in units, we should be very careful. L square by T1 by T, and this first term is the dispersion or diffusion, everything combined. As I said, it comes from Fick's law, at least conceptually. Then unit, so the concentration will be affected by the dispersion diffusion. That is first. Second is advection, as I said, and also now the source and sink terms comes. So suppose you have this. I hope I have this. I don't know whether it's discharge distance flux relation Q. Now, if you are actually, suppose you are putting something, recharging something with the concentrations. That means you are injecting some pollutants. So, that means you got a volume. So, you have a flow rate and you got a concentration. Okay. So, that is also like a sink source, but it is not only is a volume, but is also the mass, because there is a concentration. So, this is a pollutant too. So, that term is taken care of by this Q into C. See, maybe Q is the dust's flux or something, they have divided by theta, porosity, all kinds of, they do not forget about it. I mean, that is every equation is consistent. So, they are represented slightly different way, but what I say, this term is really the source of sink terms. That means, if you are taking out something by pumping, you are also losing some of the mass, some of the pollutant is being taken out. So, there is a loss of mass. So, that is a sink term, it is coming out of the system. And of course, recharging some pollutants, that is with you are some recharge with some concentration, that is also a mass that is coming in. So, that is like a source term. Okay. So, that is also included over here. The last term is, as I said, that there is reaction term. So, it might be much more than that, maybe I will expand on it. So, depending on whatever reactions are possible and whatever species you have, you might have actually loss of mass or addition of mass. It might be that you are losing maybe copper in because copper sulfate is forming, but maybe some iron compound is giving more iron or something like that. So, that is actually increasing the concentration. So, you are losing maybe copper, but it is becoming copper sulfate because it is reacting with maybe H2SO4 and copper something of copper oxide or something, but you are getting so that means it is losing maybe the copper concentration, but you are actually gaining maybe some other species. Okay. So, that those reactions has to be somehow accounted for, but again conceptually is very easy, because everything is based on mass balance. You have to find out how much mass is being created or removed from the system. Okay. So, by reactions, whatever reactions you have defined, and if you see that how much of mass is created for a particular species, that is added. If it is being taken out by the reaction, like if something is precipitating or becoming another compound, so that means you are losing that that particular compound. So, that obviously the concentration will decrease. Okay. So, that has to be taken care of. That also includes that part which is the what you call radioactive decay. Okay. Now, this does not include the sorption part. If it becomes much more complicated, if you, I mean, I will probably discuss a bit. It depends upon if you are not. So, because sorption part is there is something partitioning of the particles, either it is in the dissolved state or it is actually clinging to some of the solid matrix, then it goes to the solid phase. So, this change of phase actually. So, adsorption and sorption is slightly more complicated, and also to find out this rate of adsorption, that is also sometimes is very complex, but sometimes is necessary, because a lot of clay material there, it might actually attract some of the pollutants or something like that, and then it will be losing the concentration. So, that is sometimes taken care of in terms of what is known as retardation. Okay. Retardation and even reaction is sometimes related to retardation. So, the concentration will change because advection, which really goes from one point to another. Here it is, there is some concentration plumage here, concentration high, after sometimes you move over here. So, concentration becomes 0 here, but very high over here. By dispersion and diffusion is spreading, is going from here to here, also spreading. Then if you are source and sink terms, because you are injecting something or you are pumping out some of the water which is already polluted, that means you are losing some of the mass of one of the species or some other species. And if there is reaction maybe from one compound maybe or two compounds or two species, a third chemical species is being formed. So, there is a loss of mass. Okay. Sometimes it might be some addition of mass. So, that is also part of the mass balance condition. If there is sorption, you have to consider how much is of the species is actually sorbed or adsorbed by the solid matrix is also sometimes proportional to the concentration of the species. If the concentration very high, it will be sorbed more. It is like a sponge, it can actually absorb more. Okay. If the concentration is high, if the concentration of the species is less, maybe it will we adsorb less by the solid matrix. So, all these things are, sometimes it might cross the equilibrium limit and maybe we actually no more adsorption. So, those things are important, and whether that relationship, the amount of sorption will depend upon is linearly proportional to the concentration or is square of the concentration. Those things will determine what type of sorption model include, and it might be what is called linear sorption model, non-linear sorption model, isotherm, and this comes in the terms of isotherms. I will just mention this term and I probably not go isotherms. So, you should know whatever isotherms to use. Freundlich isotherms, Freundlich then I think Langmuir, all kinds of Langmuir is I think is the linear one, I forgot, but these are all assumptions, but ultimately these affect the mass balance condition and also how much of species is created, destroyed or actually taken out of the solution. So, that will all determine what this C, X, Y, Z, T is. Okay. So, once you can include all these things correctly, but to even know the reaction, to model the reaction process, you might need to know so many, the reaction rate, this and that. It might depend upon the temperature, it might depend on the pH value. If pH is high, it's alkaline, acidic. So, like in mine sites, we are seeing that if the pH changes from 7 to 7.5, this reaction rate is different. If the temperature changes, the reaction rate is different, and it's very difficult to predict all these things. So, things become very complicated. Okay. But then that is how, but that is the transport equation, okay, which is solved by, again, to solve it, you can solve it, you can convert this difference equations, differential equations into finite difference equations, or even finite element equations, and then solve it as a system of algebraic equations. Also, MT3DMS, there is I think multi-species transport of 3-dimensional or mass transport of 3-dimensional multiple species. So, that is MT3D. Okay. That is the model MT3D. So, mass transport of 3-dimensional multiple species. Okay. So, that or PHT3D, I think that one, reactives of reactive pollutants, that is very important, very useful. So, these are some of the software that you can actually get, and these all are contained in GMS. So, if you want to use it, so that is a very good one. If you cannot afford it, maybe you can go one by one. PHT3D, I do not know whether public domain is available, okay, but MT3DMS suddenly it is available, okay, that is available. So, now we have completed more or less a basic description of the flow and transport model, including source and sink terms. So, if you have pumping, recharge, so maybe injection of pollutants, everything can be taken care of by these equations. If you solve this, you get the value of C, X, Y, Z, T. What do you get? That means you will be able to predict or actually simulate what will be the concentration at any location at any given time. That is the solution of these models, numerical models. Again, most of the times the analytical models will not solve any complex situations, especially the boundary condition is slightly complicated, is not very uniform area. So, boundary analytical solutions almost becomes out of question. Okay. So, that is most of the time, unless a very simple system, which is not in real life situation, nothing is very simple. So, this is what there is some description of mode flow, not much, but you can look at it and look at GMS site. GMS site is actually again I say I do not have any special, I am not recommending GMS something, but as my experience GMS have been quite good, more or less. So, and I am familiar with that. That is, I think Aquavio is the vendor or something like that. I am not very sure. So, if you go to their site, probably you will get everything about GMS. Okay. And this has got so many models, 60, 60, 70, including statistical interpolation. So, this is MT3DMS is also, this is a modular 3-dimensional multi-species transport model for simulation of advection, dispersion, chemical reaction of pollutants around a system, and this is developed by Zheng and Wang in University of Alabama, but I think they developed it for EPA, US EPA, the Environmental Protection Agency most probably, and they use some finite difference methods, and MT3D is designed for use with any block centered finite difference method. That's forget about those. It is flow model. In this study, MT3D is used to compute the, that's okay, how I have taken it from somewhere. I would say that some part, not this word, but the next chapter I have taken it from one of the reports, one of not really student, but I'll tell you that part. So, this is more or less what I want to discuss for this part, but let us go to slightly more details, hopefully. That is not mine. Oh. D, is it? Oh, there is a lot of material already. No, not this one. Oh, yeah, it is. So, what are those things? NOC to the, that is not mine. Yeah. So, why D includes this? I thought that was my USB, but anyway, so how come it contains more than that? I don't know. Yeah, this is what is supposed to be there. So, anyway, there I will see afterwards. No, this is not the one. Again, I should have seen it. Not G, is it G? Yeah, this is the one. That's why I was thinking, how come I have so many things? Yeah, this is the one. Yeah, I should tell you before, because of course should be a part of the record. So, some parts I have taken is from some report by Kaniko is very Kaniko and Bredehoff. They actually developed one of the earlier models for groundwater transport, which is known as, I think, what is called MOC method of characteristic models. So, they are quite well known in USGS. So, some part I have taken from some of their reports. So, that is why I must. And the some parts every year some of the students from French university comes to my work with me for few months, and some of them are very good students. Of course, I spend a lot of time. So, they had written some reports. I have taken some parts from there. So, there might be some language problems because they try to translate from French. So, I have taken some parts. So, I should declare that, but of course, I guided them. So, that is okay. And so, they did not know where to start. They did not know anything of groundwater, but in about 4 or 5 months they did work quite well. So, I will but some parts are taken from that. So, I should actually acknowledge that part. Okay. And these are all, I will not discuss all these things. These are very similar, but it is good information, and you might find it useful. And sometimes that seepage velocity is actually specific discharge by the porosity or something. So, this is okay. But I want to draw your attention to these equations slightly in different form, because in the porosity term is on the left hand side, that epsilon term or whatever it is over here. So, it might look, but it is, you can see this is the dispersion term, this is the advection term, and this is the source and sink terms. That is what it is. If you are recharging with some concentration, that means there is a source, but you are taking out some of the water from those locations where the concentration is not 0. So, obviously, it is a sink term because you are taking that mass out of the system. But this slightly more elaborate in terms of the last term, which is the chemical reaction part, that is CHEM. So, that CHEM basically includes some of the other parts also. That is why I have here for the linear equilibrium control sorption. So, that reaction part in that equation I just put it as RK or some reaction part, but that might contain different components, and these components are that sorption part, as I was discussing, and also chemical reactions, which is rate control, that will depend on the rate of reaction, all kinds of things, and they are not easy to get. Okay. And sometimes if you do not know the rate constant to be used, their model is wrong. So, that the moment you want to include the reaction part, the model becomes very, very complex. And there are some modeling errors, and I should also tell you, because I am discussing modeling, there might be modeling error in terms of. So, when you use a simulation model, so you might be there are uncertainties for any simulation model. There can be errors and uncertainties, and these might arise due to maybe, or I should say uncertain and errors which might creep in actually. So, errors due to erroneous data, input data. So, you are giving the initial values of head, they are all wrong, some there is erroneous, some of them correct, some of them wrong, and then that creates trouble. So, therefore, that might, so you might be trying to calibrate a wrong model. Okay. So, if your data is wrong, so you have to be careful. So, what quality of data is very. So, that is data uncertainty, that might also be related to data uncertainty. So, you are not sure. Also, you may be inadequate parameter values or parameter measurements, though may be correct, but you only know the hydraulic conductivity at 3 locations in a say 5 kilometers by 5 kilometers area. So, it might give rise to errors. Okay. So, inadequate parameter measurements and also maybe erroneous. So, k value somebody has in the laboratory then does something is all wrong or sample was not corrected correctly or erroneous values. So, that is important. So, these are all part of the deal, and third part is which is important. There might be something else is not exhaustive list, is modeling uncertainty. Okay. And most of the time this is a very important, because if especially suppose that is what when I go to the reaction part of the modeling, if I do not know what is the correct reaction coefficient or rate of reaction, sometimes we do not know. You do not know what is the environment, what is the temperature, you do not know whether it will be pH will be high or low, maybe it depends upon the prediction of your pH values. Okay. So, that kind of things like in mining sites, if those are wrong. So, your the model you are prescribing to describe that process also is wrong. Okay. And you do not know is correct model is a wrong model you are using even. So, the model itself is wrong, that is big problem. And when you include this some of these complicated processes like this, adsorption, reaction, of radioactive decay is easier, because if you know the half life and all kinds of things is easier. Then uncertainty comes because you do not know whether the model which describes the process itself is correct. Okay. Because if your rate of reaction is wrong and everything, so maybe you are not even describing the process correctly. So, that is a bigger uncertainty. So, when you talk about validation and calibration, you have to remember all these things. So, how much data you have, what information do you have, you might have very good data also, but your model might be wrong, because your conceptual model might be wrong. So, then your predictions are wrong, so when what you are trying to calibrate is wrong, what you are trying to predict is also might be wrong, and that is why I said, I probably it's written somewhere, some people say you can never validate a model, you can only not validated model. So, that means you can be sure it is not validated, but you cannot be sure it is validated. Okay. So, it is not the other way. So, that is one thing. So, here also there is so many uncertain, but you have to be careful. I do not want to spend so much, but I will give you some examples probably at the end. We did some work for some mining sites and there where it is important, and the radioactive decay, that depends on the concentration also, all kinds of things. So, that is very easy. So, mass is lost by decay. So, if you account for the loss of mass, that is okay. Okay. If you expand it, it becomes slightly more expanded over here. Again, all the terms are there, but this term I have I think the bulk model density is also coming into picture. It's just a variation of the equation. You can do that. Okay. Right, rearranging the terms, but it is still the same term. And the rho with this coming because we have just a minute, the sorption part. I do not want to go into sorption part. Yes, is for decay, is for linear equilibrium control sorption or ion exchange. So, that is the bulk density of the sediment or whatever it is, bulk density of the actual material that is given is rho b, and del C by del T, the sorption rate will depend upon the concentrations in the solution. Okay, del C by del T. So, this is the bulk density and this is the sorption rate is given by this. I will not, but it will depend upon, there is a linear model, you might have non-linear model, all kinds of things are important. The temporal change in the sorbed concentrations can be represented in terms of the solute concentration using the chain rule, that is okay, del C by del T equal to del C by del T. This is just del C, that is the concentration divided by del C. Okay. That is sorbed concentration and the concentration of the species. Now, this is what I wanted to say, that therefore, the equilibrium for C bar, how much is sorbed, the concentration of sorbed particles is C bar is equal to K D into C. K D is the distribution coefficient, some people call it partition coefficient. So, there is something partition coefficient multiplied by the concentration in the solution. Okay. The sorbed concentration is nothing but K D, which is the distribution coefficient or sometimes called the partition coefficient multiplied by the concentration of that particle species in the solution. So, this is a linear model. So, how much is sorbed in terms of concentration of how much sorption will take place will be defined by this equation. That is a very simple equation, the linear equation. There might be some non-linear equation, all these things there you can, if you are, so retardation factor you can define in terms of all these things and in the density and other things. So, if you I do not want to get into too much of details, but what I want to say is that is another sorption and desorption also sometimes affects, because if some of these particles have been sopped and it has become so much sopped that is actually start releasing it plus minus. So, some of this from the clay particle or some other particles, some of the species are again released, these become desorption, and then things becomes out of control. Things are very, very complex, not impossible. But sorption sometimes not very important, but sometimes it might be important, especially if you are looking at sediment transport and other things where some of this are sediments, probably this will be very, very important. These are same equations. So, this is for decay. Again writing it in a different form. Oh, I think some part got maybe twice pasted, and there is a definition of the dispersion coefficient also. So, you can get there are various ways of doing. So, here alpha is the dispersivity of the porous medium, and dispersivity and Vm and Vn are the components. So, you can actually multiply by this component's velocity by the actually the resultant velocity, and then this is the molecular diffusion coefficient. So, this dispersion coefficient may be a summation of this molecular diffusion coefficient plus what is coming out of the dispersivity. So, dispersion coefficient is dispersivity into this velocity vectors in different directions divided by the the resultant velocity, that is V or norm V, whatever is called. So, that is not very important. You will be most of the software programs will actually calculate itself. So, but you have to give some of the dispersion coefficient, molecular and molecular diffusion coefficients generally, but which is negligible sometimes, the dm part. Okay. So, this is I want to show, I mean you can read this part, and some part is not very well written, I will confess, because I will tell you that I have taken some parts from there because I did not have time before coming. So, this is the part I want to again sing, because I was saying dH by dx, of course, this somehow I think it is in the transfer. Electronically this thing was there, but this line in between is missing. Oh, this come now. So, I do not know that's because I knew it is there, but I do not know how it disappeared. Okay, so, dH by dx at any point d is given by h0 minus h1. So, this is, if you look at it, I have already discussed this. So, I do not need to discuss again, and I hope I can find that figure somewhere. The figure is here, hopefully, or the figure is not there. Anyway, so at between 2 points, this is what it says, that how you find out the finite difference, which I have already discussed, because I am talking about the numerical modeling part, and I am just highlighting some of the portions, okay, nothing else. Wet field, this aquifer boundary is here, then you can say what is these are finite difference mesh will look something like this, and finite difference grids might like this, but these are variable grid size. Sometimes it can be all equal size, it can be different size. So, those capabilities are now there in some of the new model, numerical models. So, grid size might be also different, and also this is the finite difference mesh, how it looks like. That is just an example, and this is the study area. Maybe, okay. So, how we define it. So, sometimes you more accurately cover the study area by using this finite element. You can see it is exactly almost exactly covered, but if you use the finite difference grids, they have to be either rectangle or squares. So, you can see you have to approximate this whole area by this area. So, it will not be exactly covering the whole area properly. Okay. So, that is easier to use the finite element, but it is more accurate also. This one, yes, there is a this is a figure. This A is over here is h1, somewhere in between is 0, the h0, the head at this point is h0, this is h1, if I read it correctly, h2 over here at point 2. And in between this is the point D, in between these two is E. So, this A, this is I think, so this is A, B, and this is 1 and 2, this in between is D and E. So, this is, let us say this is 1.1, this is 0.2, this is the figure A, and this is the head looks like this. So, at this point 0, the head is h0, you can see. At this point the head is actually h1, at this point at 2, the head is h2. If you look at the other way, maybe is B. So, this is again between 3 and 4, and this f is in between, and this size is delta y, delta this is in the y direction, this is in x direction. So, basically you are looking at the grid in this direction and this direction, this is delta x, this is delta y, and these are some intermediate values. So, now what is it is doing is taking one of the intermediate grids. So, maybe this at this point you have 0, so h0, at this point you have h1, at this point you have h2. Okay. So, if you assume this, and if you take the this is delta x in this direction, this delta y in this direction, this direction is actually delta y, this is delta y in this direction and delta x in this direction. Okay. So, that is the grid size, it can be equal, may not be equal, and if you take this in between points also over here. So, that is what is taken between f and g or d and e. So, that is also delta x over here, and the same way you can do that. Okay. Now, I am just showing this so that the second derivative that I was discussing about, the del square h by del x square, del h by del x is h 0 minus h 1, you can take it between these 2 points, h 0 is at this point and h 1. So, between the difference between these 2 points, and you can find out at the middle point of this at, I think. So, that is given by this at point D over here. So, you are looking at maybe at h 1 h 0, this point is somewhere in between D. So, del h by del x or d, let us say del h by del x because partial is at this point D, at D is given by this quantity h 0 minus h 1 minus the distance between them, del psi. Del square h by del x square, as I said, that you can take now the difference. So, you can find at D, this value at D, and I can also find this value at E, and then take the difference between this thing and divide by delta x. So, you get this. Okay. So, for E, this is h 0 minus h 1, this, or h 2 minus h 0, it has E, and this h 0 minus h 1 is like at D. So, that is before. So, you take the difference between this point, divide by delta x, and you get this expression very nicely. Okay. So, if you simplify this, you will get del square h by del s square equal h 3 plus h 4, again in the other direction, because this is in the x direction, minus twice h 0, and this is h 3 and h 4, which is given in the other direction. Okay, nothing else. So, if you, and then you can write out these equations, del square h by del x square by del square h by del s square in terms of h 1, h 2, h 3, h 4 and h 0, and a is the distance between these two. So, basically is grid size in the x direction. So, a you can see. Okay, d e, and what is maybe that is a, anyway, that is the by, actually it should be delta x square and delta y square. So, this y square, okay, that is fine. So, if x equal to, so delta x equal to delta y equal to a, if you assume, then it becomes actually that delta is missing over, you do not, sorry about that, delta x is missing, but that is equal to a. So, but what it says is that you had very nice equations over here, and the smaller it is, of course, it will approximate this solution better, and you can write the same solution in not in terms of k, you can write in terms of the transmissivity, the t, which is k into b, it becomes a different equation, and these are the finite difference equations that you need to solve. So, every node may be at this point and this point and this point, intermediate points. Okay, d, e, all these things, you will be able to write this equation, you get a number of equation every point. So, then that becomes a system of simultaneous equation. Then you need the number of equations and number of unknown variables equal. For that, you might need the values to be specified at this point. These are the boundary conditions, only then you will get a solution. Okay, and what you get is the h values at different locations. Okay. So, that is, I mean, it might be slightly messy, but then please accept that it is conceptually very easy. But these are very important things to remember, that it must always remember that model is an approximation of very complex reality, and the model is used to simplify that reality in matter that captures or represents the essential features and processes relative to the problem at hand. That means, it is an approximation, and in the development of deterministic grounded model for a specific area and purpose, you must select an appropriate level of complexity or rather simplicity. That means, you have to make a judgment of what type of complex processes or how much of complexity you want to actually include. Maybe you do not have the enough of data, even then why go for 3-dimensional model, maybe you will not be able to calibrate also, or you do not know much about how much absorption is taking place, you do not know what are the values. Okay, from the field. So, why go into that, you might ignore that, maybe you are better off than making mistakes. So, and also then another point, that is also finite resolution of a model, that is in how small you make it, of course, should be more accurate, which generally yield greater accuracy. There also exists the practical constraint that even when appropriate data are available, even when, but there might exist some practical constraints, you cannot make it very small, because you might not have the values at different grid points, you might not have values like k and other porosity at every point. So, it will still be very inaccurate. And this one I want to emphasize, in general it is more difficult to calibrate a solute transport model of an aquifer than it is to calibrate a groundwater flow model. Okay. Now, generally if you go to a field situation, you will have lots of at least adequate amount of data for groundwater levels, or what we call the hydraulic head. So, maybe this location, lots of wells are there where you will get the hydraulic head measurements, but there will be many very few wells where you have the concentration measurements, okay, because that is difficult, that has to be done in the laboratory, and sometimes they are not done. So, therefore, what it says is that it might be easier to calibrate the flow model, but very difficult to calibrate the transport model, because you might not have enough data. Okay. So, that is, so you have to be careful. Sometimes we calibrate the flow model, and they say, okay, if what we are simulating for the transport part, it makes sense, if some comparison is there with the collected data, and then we say okay. But we give lot of emphasis on the flow part of the calibration, but sometimes very difficult to calibrate the transport part. Okay. That is reality, I will tell you. Okay. And this other issue that I want is grid design. As I say, the dimension of the model should be selected during the formulation of the conceptual model. If a 1 or 2 dimensional model is selected, then it is important that the grid be aligned with the flow system. So, again it depends upon the what is the principal direction. If the assumption is that one of the directions, principal direction, that x, and then is y, and orthogonal to is z. Not always possible, not that it can be assured all the time. So, but that is something what we strive for. And also to minimize the variety of sources of numerical errors, the model grid should be designed using the finest mesh spacing and time step that is possible. So, that is, as I said, that more is, I think the smaller the grid sizes are, both in terms of delta x, delta y, delta z, and also delta t. Delta t is also another grid, okay, size, the time interval, time step for computation. So, smaller it is, it should be more accurate, because it is very simple, because we are approximating in the finite difference equations. Say del h by del t is nearly equal to approximately delta h by delta t, that is h 2 minus h 1 by t 2 minus t 1 or something like that. But that is only true, this is equal to this when delta t is very small, otherwise is not that approximation. The larger it is less accurate. But then, as I said, that cannot be always assured. Okay. That cannot be always assured, because the smaller you make the grid size, more unstable the solution becomes, and then things becomes problematic. Okay. So, that is what it is. The extent possible grid should be aligned with the again that in alignment another thing, but I will show you one result, which is calibration. I might discuss a bit more, because that is very important. And mod flow and GMS, actually it can do it itself. It gives you the statistics. If you have a system, and if you have the values, that is h is known, suppose h 1, h 2, h 3. So, all this data are available, and then simulate, and actually it will compare the values that has been measured and what has been simulated, and then they will have some kind of color, this yellow or green or red, saying that whether the deviation from what has been simulated and what has been actually observed or measured is within some limit, say 1 meter, 2 meter, 3 meters, depends, and that by colors you can see that what type of fit you are getting. Okay. So, that is very useful that way, we use that. But there is another more thing, I hope I can just finish it. Hopefully, these are not important, but you can look at. There is one is called post audit. Sometimes you will have to look at, you have very small amount of data, then calibration validation does not make any sense. Maybe you have to wait for more time, for more data to come in, so that you compare, because you might think you calibrated, but only with the 2 years of data, you have separated that in some part for calibration and some part of validation. Actually, none of them are complete. So, post audit and all these things are important. Look at the data, what the results, and it's a future you should have. So, they should plan for doing that also. That is given in this flowchart. Moderate errors, as I said, I have already discussed some of the things, but this is what I am trying to say, that So, if you have plug flow, that means you have just advection. Suppose concentration is 1, but so if you have a cylinder or something like that, initially concentration very high, and then is 0 over here, the concentration is C0 and then 0. After some times, maybe at a distance, maybe after some distance it will become it becomes the same, because there is no only advection, because that concentration is traveling from here to here to here. As you can see, it becomes here and then becomes 0. So, you are measuring the concentration at this point. Okay. So, maybe initially it is this value, then suddenly it becomes 0, because nothing after that, nothing has reached that distance. Up to that, there is a continuous source, everything is C0. So, because it by advection it has reached this point, but anything beyond that is all 0. So, if you add only advection, it looks like step curve like this. Okay. So, in only advection, you have a concentration over here, continuous injection of some contaminant. So, C0 over here, so up to this it's C0, but after this is not reached any point after this. So, it is just clear break, it is C0 after this, or maybe 1.0. What is the C0 by C is equal to 1, that is what is say 1. So, C the concentration measuring at this point, and the C0 that is actually the input over here, that is equal to 1. After this point nothing has gone there, but if you have B, you have a plug flow having no dispersion, exact transport equation for transport dispersion. And if you could solve it exactly without numerical models, so just as I said, for a very simple case, for this simple case, maybe one dimensional flow, you might be able to get an exact solution in terms of some kind of function for the partial differential equation. That should be very accurate, and then that solution should be like this. But here actually dispersion is included. So, you can see it is no longer a step function like this, but it is spread like this. It is some parts actually it is becoming like this, you know. So, because some of the particles have become slower, some has become faster, some has reached more than that what is expected if you only have advection, and some of them are not reached. So, you will have not this kind of step function, but you will have theoretically, which is correct with dispersion, anyway a model like this. Okay. A breakthrough curve profile like this concentration. Okay. Concentration curve will look like this, not a step function over here, not like this. So, because some of the particles will move faster, some slower. But interesting part is actually see the numerical solution, how does it compare. You see it may not actually match because of many other reasons, that it might not be fitting in the exact curve, it might be somewhat different. That you can see C is the curve which is that do not expect that it will be exactly matching so this B, this is C, I can see there is a difference. Numerical solution versus case B, effects of numerical dispersion. So, that means there are some effects, maybe the dispersion is more because there is a numerical dispersion, as he said that sometimes the dispersion comes due to numerical reason. There is more dispersion, and as you can see it is spread more, this concentration is lowered over here and it is spreading like here. Okay. This is the case C. That means numerical dispersion which is giving artificial dispersion, and therefore, the result is you can see the concentration is spreading. So, you have to be careful. Okay. So, that is why I said that concentration calibration. And D is if it starts having oscillations. So, the same numerical model is oscillating, maybe your solutions will not like this, but it is like this, as I see that, and then these are very inaccurate. So, it might be due to the grid size, maybe it is too small, or because some other reasons that your solution is not correct, is not converging. So, now if you are trying to accept say D and then trying to calibrate and validate, it does not make any sense. Okay. So, these are very important subtle points. So, you should remember, and this more or less there are some other important issues I should say, because this is good to read, mass balance and other things, conditions, calibration criteria, some other things. And one thing it says that you can never validate a model, and there is lots of references, and there are some examples also. You can actually, I might discuss a bit of this. So, this is the calibration results we had, actually is for a real site we had, and we had to do a lot of time, maybe I will discuss a bit of it in the next class. Okay. So, I think we are more 5 minutes is okay, over, I think so. Anyway, so I might discuss that example problem, but we have done work on a number of mine sites and one urban polluted site where there is a leaking petroleum pump tank. So, I might be discussing those values. Okay. And also some saltwater intrusion problem if I find time. Okay. Any question? Did I go too fast or nothing understandable? It's okay. Anybody has any complaints? Okay. Yeah, stop me if I am. Sometimes I get carried away by some of the things, and I am thinking something, and maybe I do not explain.